All right. So let's do some questions here. It sounds like, by and large, everybody wants to talk a little bit about 28 at least. So let's do that kind of to start. All right. So the first thing I'm going to do is I'm going to define vector u into the component form. Okay, with that? So u dot u then would be u1 comma u2 dot u1 comma u2. So that's just by definition, right? That's how we define my vector u. Now, to take a dot product, what we do is we multiply the first components together and then add it to the second components multiplied together. Everybody okay there? So if I just simplify that, then I have u1 squared plus u2 squared. Everybody's okay there? Now, to explain what I'm going to do next, remember the definition or the formula for magnitude is this, right? Everybody agree with that? So magnitude squared would be this thing squared, right? What happens when I square a square root? They would cancel each other, right? Which is exactly what we have here. So what I can say then is that this is equal to that, which is the magnitude squared.
So that was just Couldn't you just say, by the law of magnitude, says vector u times vector u is equal to the value of vector u squared, and on 28 it's equal to vector u squared. Since that's equal to vector u times vector u.
Okay, so I think I think you're using the theorem to prove the theorem.
So you're trying to prove the theorem of
yes. 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 So it's like using the word to define, like the definition of a fish is it's a fish, right? Like same kind of idea there. So typically you start on one side and then you work to make the other side. So that's typically what a proof format is, like an algebraic proof like this would look like. So again, what we did is we started with u dot u, and we worked algebraically to turn it into magnitude of u squared. Which is, you could have started on the right side and gone to the left side, but that's a little bit less obvious as to how to do that. But there's nothing wrong with doing it that way either. So you guys want to do 25? Okay. So this is u dot v plus w equals u dot v plus u dot w. So first things first, I'm going to define my three vectors into component form. Everybody's okay there? Then I'm going to start on the left-hand side and try to end up at the right-hand side. So the first thing I'm going to do is I'm going to replace these vectors with their component form definitions. Everybody okay there? So I'm going to follow the order of operations now and work inside the parenthesis first. So how do I add two vectors that are in component form? I just add the components, right? So that vector is going to turn into v1 plus w1, v2 plus w2. Everybody okay there? Now I'm going to use the definition of a dot product. So the dot product says I multiply the first components together and then add that to the second components multiplied together. Everybody okay there? So now it seems obvious that the next thing I should probably do is to distribute. So I'm just going to distribute these u's. Notice that this is not the distributive property for vectors that I'm using, because u1 and u2 are components, they're just real numbers. So I'm just using this distributive property for real numbers here, not the distributive property for vectors. So it's okay to do this. We okay to here? And now what I want to do, if I look at where I'm trying to get to, go back and check that one more time. I want to get u dot v and u dot w. So what I'm going to do is I want to group the stuff that has the v's together and group the stuff that has the w's together. So if I look here, these pieces have v's in them, and these pieces have w's in them. So I'm just going to group those pieces together. And it's okay to do that because, again, these are just real numbers and I can change the order of addition for real numbers. That doesn't make a difference. And now I'm going to use the definition of a dot product, but kind of going in reverse. So this guy would have been u1 times u2 dot v1 v2 right? Because when I do the dot product, I can multiply the first components and then add it to the product of the second components, which is just what we've done. Then I have my plus sign. And if I look at this one, this would have been u1 comma u2 dot w1 comma w2. And then if I use my component form definition, that's u dot v plus u dot W. From here to here? Well, in the beginning we defined U1 as U1, or U as U1 comma U2, right? So that's all I did there. Just switching it back. Yep.
So essentially they're all
component form and then turning it back at the end. Yes, that's absolutely what we're doing. And it's a very common technique when dealing with vectors in general, is I take my vector, put it into component form, do all my arithmetic in component form, get my answer in component form, and then switch it back into my normal vector notation.
That's the only way to do it.
The only way to do it, you could have done this geometrically, but this is by far the easiest way to think about it. As far as these proofs go. Does that, I know these are hard, but is this okay what we did? Able to understand how I've moved from one step to the other? Do we need to go back and look at anything anymore? Were there other homework questions that you want to talk about? I know that these two were skipped frequently, so I want to talk about those, but I'm happy to do others. Kendall?
I'm just confused about when you get to the vector form, but you still have that square root 2.
Yeah. Should we do it?
Sure.
Okay. So the first thing I'm going to do is I'm going to rewrite CB and BD in component form. So remember our definition for component form was like x2 minus x1, y2 minus y, right? So the C is my x1, y1, and my B is my x2, y2. So C is the point negative 2, 9. And B is the point 5, negative 4. So BD is the component form vector, negative 7, 13. We okay with how I did that? So here again, B now, since it's the first letter, is my x1, y1, and D is my x2, y2. So D is negative 1, 6, and B is 5, negative 4. So I have that. Okay. So now if I go ahead and plug these back in fact, it asks for the component form. Well, I guess it wants the magnitude of the vector. Okay, never mind. So that's fine. So next I have negative 5 times the component form for CB. Maybe I should write that 13 so it doesn't look like a B. Plus square root 2 times the component form for BD. Okay, there. Okay. So now I'm going to go ahead and do my scalar multiplication because the order of operations says I should do multiplication before addition. So 5 times negative 7 is negative 35, and 5 times 13 is 65. Negative 6 times the square root of 2 is negative 6 square root of 2, and 10 times the square root of 2 is 10 square root of 2. Oh, yeah. So that should be positive, and this one should be negative. Thank you. Everybody's okay there? All right. So if I add these then, I can't add them directly because one of the numbers is rational and the other is irrational because one has a square root in it, the other one doesn't have a square root of 2 in it, so you can't add them directly. So this would be your component form answer, as it would look like this. Okay with that? So that's our the component form. It also wants the magnitude of this vector. And this is going to be a messy pain in the butt to do by hand, but we'll do it by hand anyways, and then I'll go and show you doing it, typing into the calculator and getting the calculator to give us an answer. So remember, for a vector in component form, its magnitude is the square root of the first component squared plus the second component squared. Right? Now, why is this going to be a pain in the butt? Because we have to FOIL out the 35 minus 6 square root 2 squared. That's really a FOIL problem. So like, just to write this out, normally I won't do this, but just to illustrate what's going on since it's still quite early on. 35 minus 6 square root 2 is really the same thing as 35 minus 6 square root 2 times 35 minus 6 square root 2. So we'd FOIL this. And I'm too tired at this point to do 35 times 35 in my head. That just isn't going to happen right now. That's 1225. And then 35 times negative 6 square root 2 is negative 210 square root 2. And I get that twice, once here and then once there. And then I have plus 36 square root 2 squared, or really just 72. So if I combine that stuff all together, I get 1225 plus 72, which is 1297, and then 210 root 2 minus, or plus 210, I'm sorry, negative 210 root 2 minus 210 root 2 is minus 420 root 2. And then I have to do the same thing for negative 65 plus 10 square root 2. So again, got to FOIL this all out, and I'm still too tired to do 65 times 65. I know they're negatives, but when you multiply the two negatives, you get a positive, so it doesn't really matter. So 4,225, and then I get negative 650 root 2 minus 650 root 2 plus 100 root 2 squared, or just 200 there. So that's going to give me 4425 minus 1300, excuse me, root 2. Okay, so this is going to be 1297 minus 420 root 2 plus 4425 minus 1300 root 2. So when I combine this stuff together, I don't want to do that in my head right now either. I'm too tired, guys. Who's ready for a nap? You and me both. I hope if I type this in right. 1297 plus 4425. 5722 minus 1720 root 2. So that would be my magnitude. Now, to be honest with you, I don't care if you gave this to me as a decimal rather than this. And it's much, 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 much easier to just have your calculator do this. So let's just, again, show you that real quick. Oops. So all I'm going to do is I'm just going to type this into my calculator. So I'm going to do the square root of 35 minus 6 root 2 squared plus negative 65 plus 10 root 2 squared, and I get about 57.35 would be fine. That was a lot of stuff here, Kendall. I apologize for doing this maybe the most excruciating way possible, but
I'm sorry.
huh? Which number was this? 18? Oh, that's not what I have written down as my answer. Oh, maybe I just have a negative sign dropped. Oh, were you trying to tell me? No, that negative 5 should be there. I don't know. I think I screwed up the answer key. Anyways, whatever. You get the idea, right?
Yes, I can get it.
Yeah. Maybe I don't know. There's either the answer key has a mistake in it that I was looking at, or I made a stupid arithmetic error and dropped a negative sign somewhere. The fact that when I looked at the answer key, I saw 2 drop negative signs kind of makes me think I just screwed up the answer key and not the other way around. But, I mean, it's entirely possible. Who the heck knows? Oh, I bet I know what I did. Anyways, moving on. I think I screwed it up. Yeah. This time. So I wrote the formula down correctly here, but
I was gonna say something, but I didn't say anything.
What's the actual answer?
So this is, I said was x2. I put x2 here.
I was gonna say something. I had it.
And this is y2, and I put y2 here. So I goofed that up. Yeah, I mean, I wrote down the right.
I wouldn't have gotten it right because, but.
Can you tell me the actual?
Yeah. So. So the only difference in the answer where these signs are opposite of what I wrote. And then were those other signs up? No, those other signs were right.
Well, actually, you know what?
And then when we get the magnitude, then that's mega wrong.
Can you solve the x value? Just in your calculator.
Oh, sure. Yeah. And again, I probably wouldn't have minded had you given me a decimal there, unless the directions specifically ask for an exact value.
I think it is.
Oh, good. Cool. That's 1.
I'm assuming. Well, I got 79.14.
Yeah. Good job. Other questions from this? My apologies for goofing up on that one. I thank you for that. At least I caught it by the end where I'm like, oh no. Look at what dumb things I did.
That's one thing about taking notes.
Yeah. But Kendall, I would say in general, if you see me something that you think is wrong, say something. It's okay.
I just
Worst case,
stuff, so I was like, I don't know.
If you say it and then you're wrong, you're just like,
And then
But-
I was like, I'm a little embarrassed.
but that's okay. Like if you say something, if you think something's wrong and it turns out not to be wrong, it's probably because you didn't understand what was going on. So it's not a bad idea to stop and have me like re-explain why what was going on was correct, right? And if it is a mistake, certainly it helps everyone to stop the mistake before it goes too far and it becomes what happened
The
here.
biggest thing is on that problem, you have to know the values of each letter, and I didn't know.
yeah.
So you would assume.
Yeah.
If I had the problem written down, I would have known.
Oh, yeah, you would have seen the mistake that I was making.
I
Yeah,
would have known which one was X1 and X2.
I see. Yes.
Chill for the rest of the class.
No, I mean we're gonna do some stuff. We still have like 35 minutes
Hear me out
left.
though, like what if we didn't? And you could finish your cherry Pepsi.
I can finish my cherry Pepsi and do more. That is not a problem.
You have to appreciate it. Appreciate the engineering.
Oops. All right, so let's pick up where we left off last time. I should have dated today's. All right. So,
How many sections are we doing today?
we're probably gonna, we'll finish section 2 that we've been working on. We didn't finish section 2 yesterday.
We're in section 2. I
Okay.
thought we did like 8 sections yesterday.
Recap.
So let's start with a little bit of a recap then. If everybody feels like we've done a ton, that's fine.
I mean, I know it happened. I just felt like that was a lot for 1 second.
But yeah, I filled up 2 pages of notes for 1 second.
Yeah.
Yeah, I just I don't understand
That
this.
doesn't happen that often.
So
How many
let's,
sections are there?
that we're gonna do in this chapter? Maybe 3, maybe 4.
So we're almost getting to a test.
I mean, we're going to take some time and do some like in-class practice stuff, but
We take a partner test.
we did one of those last year, but it was the very last
Those
test.
are final.
Yeah,
Let's save that.
Dude, the partner test was rough.
Yes.
Just because, like, you want to, like, you don't want to be with your friends in that point. You can't just tell your friend. Like, I couldn't look Justin in the eye and tell him that I did not want to.
That happened to me in John, and my friend was like, "Hey, you want to be partners?" And I'm like, "No, I absolutely do not."
I couldn't. I just suddenly confused that you're not asking. I was like, how do I say it? I want to do.
All right. So in section 1, we talked about how to convert back and forth between the 2 forms of vectors. So there's 2 ways we can represent a vector. One of them is in component form, and the other is with a magnitude and direction. So to go from magnitude and direction back to component form, we take the magnitude of the vector times cosine of the direction. That'll give us the x component. And then we do the magnitude of the vector times sine of the direction, and that gives us the y component. To go from component form back to a magnitude and direction, we can calculate the magnitude by taking the square root of the sum of the 2 components squared. And then the direction, if we graph the component, we're looking for this angle. Now what we're going to do is we're going to find this angle that I'm going to call alpha by doing the tan inverse of the y component over the x component. And then what I'm going to do to find my direction then is either I'm going to add that alpha to some multiple of 180, or I'm going to subtract alpha from some multiple of 180. So I'll write that as k times 180 plus or minus alpha. Now remember what I had told you was when drawing the direction, if the last axis you passed through, getting to the terminal side of your angle, was the y-axis, you're going to subtract. So in this case, you would have done 180 minus alpha. If the x-axis was the last axis you passed before the terminal side of your vector, then you'd be adding. Okay? Does that kind of refresh our memory here a little bit? And that was basically the gist of section 1, was just about how to convert back and forth between these two forms of vectors. Okay? In section 2, we talked about adding and subtracting and scalar multiplication, dot product, and unit vectors. So if I have a vector u and a vector v, and nope, this is still what we did yesterday, and some scalar, I can calculate u plus v by doing u1 plus v1, and then u2 plus v2. I can subtract the two vectors, u1 minus v1, u2 minus v2. I can scalar multiply, so the scalar just multiplies the first component and multiplies the second component, and my result is still a vector for each of these three operations. We also talked about the dot product. Here, what I do is I multiply the first components together and then multiply the second components together and add them. Here, the result is a scalar. So the dot product of two vectors is a real number. It's a scalar. It's not a vector quantity anymore. And then the last thing we talked about was unit vectors and the formula that we had there to find a unit vector in the same direction as vector u. We take vector u and we multiply it by the scalar 1 over the magnitude of u. And the result will be a vector with magnitude of 1. So that's kind of the recap, just a quick 5-minute recap of what we've done so far. And you're like, it seems like we did way more than that, but a lot of it was building up to these ideas. This is just summarizing what we had built up. So these are the details that you'd really kind of want to be familiar with and what are going to be the useful tools in kind of doing these problems. Okay? So let's start by doing an example. Let's say that we have vector u, that's 2, -3, vector v, that's -1, 5, and vector w, that's written as 8i plus 4j. And we want to evaluate the following. We're going to do u dot v. We're going to do w dot v. We're going to do 5w dot u. And then we're going to do u minus w dot 2v. Okay, so let's start with u dot v. This should be relatively straightforward. So I'm just going to take the x component from u and multiply it to the x component from v, and then add that to the product of the y component from u times the y component from v. So I get negative 17. Is everybody okay there? That should be pretty easy, right? Just a little bit of computation. Nothing tricky going on there. All you really had to remember was your dot product formula, right? Next up, we're asking to do the dot product of w and v. Now, w is written weird because I don't define what I and j are, right? The reason I don't define what I and j are is because these were the standard unit vectors. They're always the same vector. These are things that are like facts that we'd want to remember. I is the vector 1, 0, and j is the vector 0, 1. So this is really the vector 8, 4. So I'm going to think about vector w as really just the vector 8, 4 throughout the rest of these example problems. That's all just a different way of writing a vector rather than writing it in component form. We can write it as the sum of these two standard unit vectors. So if I do that, we have the x component from vector w times the x component from vector v plus the y component from vector w times the y component from vector v. So I just get 12 there. Everybody okay there? All right. If we go on to C, notice that I have a scalar multiplication going on there as well as a dot product, right? We're multiplying by 5, and we're taking the dot product of w and u. The question becomes, what order should I do these things in? Well, according to the associative property for dot products, it doesn't really matter. You can multiply the 5 to the w and then take the dot product. You can multiply the 5 to the u and then take the dot product. You can multiply, or you can dot product the w and the u and then multiply by 5. It doesn't really matter. Is everybody okay with that? I'm going to choose to do it that third way. So I'm going to take the dot product of w and u and then multiply that by 5. So the dot product of w and u is the x component of w times the x component of u plus the y component of w times the y component of u. So 16 minus 12 is 4, and 5 times 4 is 20. Is everybody okay there? So the last problem here, we have a difference of two vectors, a dot product, and a scalar multiplication going on all at the same time. So what order should I do things in? There's one thing I must do first, and that's the part in the parentheses. So I can clear those parentheses by doing one of two things. I could subtract the two vectors, or I could distribute the dot product across. I don't know any reason why I'd want to distribute the dot product across because it kind of makes more work for myself. I'm just going to subtract the two vectors because I know exactly what these two vectors are, and it's not difficult to do that subtraction. So u minus w is going to be 2 minus 8, and then negative 3 minus 4. It's going to be negative 6, negative 7, dot, negative 2, 10. Then to do the dot product, I just do negative 6 times negative 2 plus negative 7 times 10. So I get negative 58 at the end. Does everybody feel okay doing these kinds of little computations? Not too bad, right? Should be relatively easy. So our next formula here in section 2 continued. The angle theta between two vectors is the cosine inverse of the dot product of vectors u and v divided by the magnitude of u times the magnitude of v. So, as an example, I might ask, what is the measure of the angle between vector u and vector v? So there's three things that I need to know to plug into this formula. I need to do u dot v, so that's going to be 7 times 2 plus negative 6 times 2, which just gives me 2. I'm going to need the magnitude of u, which is the square root of 7 squared plus negative 6 squared. So that's 49 plus 36, which is 85. See you later. Yeah, check Power School. It'll be up there by the time you get home.
Okay.
You're welcome. And then I need the magnitude of vector v. So that's going to be the square root of 2 squared plus 2 squared, or just the square root of 8. Everybody okay with what I've done so far? So now I'm going to plug these into the formula. So I'm going to have the cosine inverse of 2 over the square root of 85 times the square root of 8. Now, when I type something like this into my calculator, I like to use the fraction command to make it a little bit easier to get into my calculator. So you can access the fraction menu by pressing the alpha button and the y equals. In a case like this, we just want the first option, numerator over denominator. So what that allows me to do is to type this into my calculator exactly like it looks on my sheet of paper, which makes it much harder to like mess up the parentheses or whatever. Caitlin? You're good? Okay. Thanks, brother. I love it. So that gives me 85.60 degrees when I type that into my calculator. Well, I have one little thing left in this to close this section out. We say two vectors are orthogonal if the angle between them is 90 degrees. What that then says is that two vectors are orthogonal if and only if u dot v is equal to 0. Actually, we should probably call that a theorem. So to show these two vectors are orthogonal, all I need to do is compute their dot product and show that that's 0. That's a 10. So that's going to be negative 5 times 16 plus 8 times 10. Negative 80 plus 80 equals 0. And we're done. Look at that timing.
Let's stop everything here at the end of the day as we lift up our hearts and minds to God. In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Is there someone who is sick or in special need that I would like to lift up to God in prayer right now? Or maybe a law enforcement person? God of salvation, remind us always of your great love for each of us. In the name of the Father, and of the Son, and of the Holy Spirit. Amen.
Chelsea. Bye, Mr. Coolin.
Bye.
Dig me.
Yeah.